Continuing with our cavalcade of electrolytes, we looked at sodium. Now here's potassium. You know all about potassium. I mean, we've been talking about potassium all throughout Bio 201. You know, the concentration gradients are what drives the action potential. Sodium-potassium pump determines potassium concentrations. And look at all the different foods that are high in potassium. Potassium. And these are giant drying fields. This is near Moab, Utah. There's a huge potash mine there. Potash has potassium chloride and other compounds, potassium nitrates and things, but mostly potassium chloride, I guess. They mine it. They force water into the ground and produce this like slurry, in certain areas, and then they get this stuff that's really high in potash. And that name comes, by the way, from the old days of taking plant stuff in a pot and adding water, and yeah, very high in potassium. So I drive by there every year. Those ponds are the size of several football fields. You can't tell the scale from this. Those are massively huge ponds. And they have their own little railroad tracks there, and they have railroad cars, and they load the potash into the railroad cars and it gets shipped out. It goes all over the world. But I drive past there at one point, and the ponds are all fenced off. They don't want people screwing around out there. But there are delivery trucks that, go back and forth between the ponds and the railroad cars. And so there's chunks of potash lying all over the ground. So I picked one up and brought it back to show you. It's like a size of like a ping pong ball. It's like a big chunk of like hard rock salt, which is what it is. So remember potassium homeostasis, so 90% in the glomerular filtrate is reabsorbed by the PCT. Remember, the PCT did 2/3 of all your reabsorption. Most potassium forced out and brought back in right there, okay? DCT, a cortical portion, secrete potassium response to blood levels. So aldosterone then, remember aldosterone is the hormone that causes you to save sodium, but at the same time causes you to excrete potassium. So that's why hyperaldosteronism could lead to both hypernatremia and hypokalemia. Think about that. That makes sense, okay? You're going to get rid of potassium and save too much sodium. Potassium imbalances are really difficult to understand, and I basically don't understand them, so I'm just admitting that right now. Most dangerous imbalances of electrolytes. There are some other pretty dangerous ones. Calcium can be really dangerous. Sodium, dangerous. But potassium, they say, really messes acid-base and some other things. So potassium imbalances are really critical. And here's where the problem comes in. So hyperkalemia, too much. Remember, potassium is the main cation of the intracellular fluid. So it's inside of cells. So it's not supposed to be a major cation of the extracellular fluid, and if it becomes one, that's problematic, okay? Now, the effects of that depend on the rate of the imbalance, whether it comes quickly or slowly. If it's a rapid onset, like a crush injury, then you get this increase in nerve and muscle excitability. So, because remember, potassium inside the cells, like in a crush injury, which is what you see in the upper right, looks like that's a laceration. Well, there are lacerations, but that was caused by the person's hand being crushed. The skin just popped and the bones crunched. And so what's going to happen is all kinds of cells are now lysed. They're physically forced to burst. And so they're going to release massive amounts of potassium. So you get a sudden onset of hyperkalemia, all right? If slow onset inactivates voltage-gated sodium channels and nerves become less excitable. So hyperkalemia can lead to either hyperexcitability or hypoexcitability. Depends on the rate of imbalance. I think in the nursing schools they really talk about just how to treat it. Forget about understanding it. Just learn how to treat it. Hypokalemia, sweating, chronic vomiting, diarrhea. A lot of the bulimics end up with hypokalemia. Nerve muscles less excitable, muscle weakness, loss of muscle tone, depressed reflexes, arrhythmias. So these people are going to be not very active, all right? They're going to be struggling. Chloride. So chloride, we've talked about chloride a lot. We know about chloride. Remember, it's the main anion of the extracellular fluid. It goes wherever sodium goes. So, yeah, it has an effect on osmolarity because it's always out there with sodium. So, remember, you have to use it to make hydrochloric acid in the stomach. Chloride shift, we're in the red blood cells. So we've seen the chloride shift a few times now. pH, regulating pH, obviously. Acid. Okay. Oops, I talked over the break again. Yeah, so here's the bottom line is that you don't really have to care about chloride. Sorry, that slide went too fast. Whatever imbalances are caused from chloride, generally, since chloride goes wherever sodium goes, you're going to have the same imbalance in sodium. And turns out the sodium imbalances are more critical than the chloride. So bottom line is, yeah, chloride imbalance is serious, but sodium is going to be more noticeable and more serious, so you don't have to worry about it. Hyperchloremia, yeah, set the saline wrong, leads to acidosis. Hypochloremia, yeah, result of hyponatremia, okay. pH imbalance is just going to go with sodium, all right. So, and the alkaline diet, okay. And then the cute little nursing school thing, binder, ring binder, so cute. If you go down, I'm going down with you. Oh God, that's just, let me out of here. Calcium, we know a lot about calcium. We've been talking about calcium homeostasis since the very first part of Bio 201, all right? So everybody should have this really solid, and if you don't, now's the time to get it, okay? Just think back, all right? Get your old notes out. Let's take a look. What are the things that calcium does? So remember, calcium is what makes your bone. You have the matrix in your bone is made of collagen, a protein, but then it's filled in with hydroxyapatite, a calcium phosphate mineral. Muscle contraction, remember calcium had to move the troponin tropomyosin complex out of the way so the myosin head could bind on the actin filament. It's an important second messenger, all right? Remember GPCRs and stuff like that? Calcium functions as a second messenger throughout the body. Exocytosis, so remember neurons don't release neurotransmitters unless there's calcium. And blood clotting, remember that was part of the blood clotting series of reactions, all right? So the whole cascade of blood clotting. So calcium, yeah, it's pretty damn important. So how does homeostasis work? We know about this. Here's where we studied in Bio 201. PTH, parathyroid hormone, raises blood calcium by stimulating bone resorption by osteoclasts. Remember osteoclasts, the cells in the bone that break down bone. They return then, they release calcium, which returns to the blood. PTH stimulates that, okay? Calcitriol, also vitamin D, all right, raises blood calcium as well by stimulating bone resorption by the osteoclast, just like PTH. But the big deal with calcitriol, vitamin D, is it helps you absorb calcium in the small intestine. So dietary calcium, calcitriol really helps that. And of course, that's why, who drinks milk mostly? Who should be drinking milk? Yeah, little kids who are growing. And so how do you make vitamin D? Remember, you go outside. Well, what if you don't go outside? Well, that's why the Dairy Council or whatever now approves virtually all milk sold in the United States is vitamin D fortified so the kids don't get vitamin D deficiencies, get rickets and things. Calcitonin was the third big calcium hormone, but remember it does the opposite of PTH and calcitriol. So it's mostly a factor for children, not adults. This is when kids are growing. So what does it do? Lowers blood calcium by stimulating bone deposition by osteoblasts. So remember, osteoblasts are the cells that grow the bone. Bone deposition, they're making bone. So yeah, kids are growing. They need to make bones. So that's what calcitonin does. It says, get all this calcium out of the blood and put it in the bone, damn it. That's where it needs to be. So cells normally keep not much calcium inside because it tends to crystallize, and you don't want crystals inside your cells. I mean, maybe if you're new age, you do, but you really don't. Phosphate levels high in the ICF, yeah. With respect to calcium imbalances, remember we're mostly going to have either too much calcium in the blood or too little calcium in the blood. So let's start taking a look. Hypercalcemia, too much calcium in the blood. What might cause that? Well, how about hyperparathyroidism or hypothyroidism, all right? So hyperparathyroidism, parathyroid gland makes parathyroid hormone that raises blood calcium, right? Hypothyroidism, all right, so calcitonin from the thyroid normally would lower calcium, and so if you're not secreting enough, you're going to end up with hypercalcemia, all right? Consequences, again, depresses membrane sodium permeability, inhibits depolarization. So what do you get then? Well, you don't get good action potentials at the muscles, so you get muscle weakness, all right? Muscle weakness, depressed reflexes, cardiac arrhythmias. Remember, the cardiac muscle potential was prolonged by calcium. Remember, the rising phase was sodium, but then calcium prolonged the contractions. So you mess with calcium, you end up with cardiac arrhythmias. So you can see calcium imbalances pretty damn serious. Hypocalcemia, the opposite. What might cause it? Not enough vitamin D, diarrhea, too many solutes are leaving your body, pregnancy, lactation. Pregnancy, a little parasite, stealing all of your nutrients. Lactation, they're still stealing your damn nutrients. Even you finally squirted them out and they're still stealing nutrients from you. Hypoparathyroidism, hyperthyroidism, just the opposite of what we saw above. In other words, before we raised calcium, now we're lowering calcium. Consequences, increased membrane sodium permeability, nervous and muscular symptoms abnormally excitable. So yeah, remember, calcium, hypocalcemia, this is the really serious one where muscles can start locking up. You got Trousseau's sign or carpal pedal spasm because the forearm flexors more powerful than the extensors, so you tend to flex, contract all the fingers, the metacarpals. Very low levels result in tetanus, in other words, where all your muscles are now locking up. Laryngospasm, so your throat is now locking up, and death. And I'm pretty sure I told my Bio 201 people the story of my former student who watched someone die of laryngospasm in the emergency room. They couldn't even get the person intubated and stuff. The muscles just... What do phosphates do? Well, we know a lot about phosphates. We've been talking about phosphates for a long time. Let's just go ahead and note everything that's true here. So the phosphate ion, remember all the different forms, just how many hydrogens are attached. Name the hydrogens and you're done. Nucleic acids, remember? All right, the very essence of life, of the instructions of life, okay? Phospholipids, so cell membrane. ATP, GTP, cyclic AMP, incredibly important. ATP, of course, for energy. GTP, so many metabolic processes involve GTP, ATP, cyclic AMP. Creatine phosphate in the muscles, hydroxyapatite makes up your bones, so clearly phosphate, an essential deal. But the great thing about phosphate is you have this massive reservoir of it in your skeletal system. So as a result, it's usually easy to maintain phosphate levels because you just, either bone deposition or bone resorption. So, and remember then, whereas bicarbonate was the buffer of the extracellular fluid, the phosphate ion is the buffer of the intracellular fluid. So what controls phosphates? Do you remember? We talked about this before. We mentioned this before. So we have, remember I told you because of the sodium-potassium pump, sodium-potassium often go different directions in the body, all right? When sodium goes one way, potassium goes the opposite way. In terms of cell membranes, one's going in, one's going out, whatever. Remember I told you phosphates also tend to go with somebody else. Who goes with phosphates? Yeah, calcium. So generally speaking, they go opposite directions, all right? So if plasma concentration of phosphate drops, renal tubules reabsorb all filtered phosphates, so very easy to control by the kidney. Parathyroid hormone will increase the excretion of phosphate. At the same time, it raises blood calcium levels, all right? Basically, it's going to hold in calcium, all right? We're trying to raise blood calcium. It's going to cause phosphate to get excreted. So phosphate and calcium often go opposite directions. But that's great because that gives your kidneys an easy way to control it, all right? You control excretion of phosphate as needed, all right? And again, your body can tolerate huge variations in phosphates because you've got this massive reservoir in your skeletal system, okay? Which of the following most likely to cause tetanus? Remember tetanus. We're not talking about the disease. We're talking about the meaning of the word from Bio 201. Remember, muscle means a muscle contraction. So what's going to cause muscle contraction? Hypocalcemia, hypophosphatemia, hypokalemia, hyponatremia, or hypernatremia. So make sure you know your ions with respect to the causes of their imbalances, okay? Or the effects, both causes and effects of imbalances. In this case, hypocalcemia. Hypercalcemia, remember muscle weakness. Hypocalcemia is hyperexcitability, sorry. Hypocalcemia leads to hyperexcitability, including Trousseau's sign and laryngospasm and the whole works. Okay, kids, I'll see you next time. And here I am at Toro Week. I'd hiked partway down. I'd hiked down from the point, and then there's no trails. You just, rock hop your way, and then you get to places where you can obviously climb down. So you go partway down into the canyon, look around. It's awesome. You can see the lava flow there to the right. That's where Lava Falls is on the right side.